Good afternoon. My name is Brian. I'm from H3 platform. We have been doing PCIe expansion box disaggregate. We're starting from the Gen 3, and now we build up a Gen 4. So later on, we will explain a little bit of the functional feature of the box, and then we do the demo, and then we go back to the architectures. So then you understand why we build up this box and where it's been used. I think it's this is a new trend because I think it's. I will start first from the motivation. I think the motivation. I use the IBM's Watson's lab because they have been doing the POC from PCIe Gen 3 with us, and then they are going to deploy Gen 4 for their usage. The usage is because Watson have plenty, like 50 people doing the AI. And then that AI has a very different requirement. For example, if you do the voice AI, you need one CPU to one GPU. You have lots of data processing in the CPU, then go to the GPU to offload, then go back to the CPU. And then you have the image. If you do the image, you need like 4 GPU and 1 CPU. To do the a lot of image recognitions. But if you do the AI, especially image AI, you probably need 1 to 8. So there is so many diverse requirements. And the key problem is that you usually cannot ask the researchers, say, hey, please use this machine, and then next day say, hey, please use that machines. It's very difficult for them because they have the data, they have the algorithm. They stay in one machines. They don't want to change. So the problem is that how you can manage all this requirement. The only thing that you buy a lot of machines, but they say no, we don't buy so many different 1 GPU server, 2 GPU server, 4 GPU server, or 8 GPU server. They just buy a server plus lots of the server plus this is our Gen 3 products. So it will come out like this. It's a dynamical allocate all the different GPU to the server to do the GPU composable systems. That's the AI composable AI motivations in this part. Yeah, since we have a small group, so feel free to ask any questions during the presentation because if you have any questions, it's easier that. Yeah, please.
I'm going to assume that reconfiguration takes a server reboot. Is that a fair statement in Linux?
No.
No?
After Linux 3.7, the Linux PHP, Linux hard plug has been fully utilized, PCIe hard plug.
But the NVIDIA graphics GPU?
Oh, good questions. There's a certain level of a hard plug. So let's step back a little bit of the storage hard plug. Storage hard plug is no matter you are accessing or you are reading, you just can plug the drive. No matter it's NVMe, SAS, or SATA, any drive. But in GPU, it's not. In GPU, it's in various environments when they are starting to use the CUDA to map in all the device memory and to map in the system memory, he need to know all the devices where it is and to mapping it. And then when he run it, when you call CUDA library, so he will transfer all the data in between all their memories. It's not allowed to get in of any GPU or get out of any GPU during the process is running. Yeah, still, if it's running, then it's just stop. It's hand there. It's not kill the systems, but it's just don't work. So what we do is that the driver is not working, then we do the hard plug, the GPU. Then the driver will remount it, and the CUDA will see all the device memory. So the hard plug is that you don't need to reboot the system, but sure, you need to stop your process, and then restart your process. So. No need. You just need to, the driver will recognize it by itself, but the CUDA won't. So usually, yeah, CUDA won't. So usually normally you will use the CUDA library.
There's a command for CUDA to reconfigure
No, NVIDIA don't support it. I think they don't support it. There's some reason. The reason is that because he want to optimize the memory mapping. So, I mean, the old GPU device memory and mapping to the system memory. So it's easier for them to do the backward synchronization, forward synchronization, that kind of things. So so they need to topology away and topology fixed for the CUDA in order to optimize. If you don't fix it, CUDA is very difficult to optimize that kind of things. So that's why the CUDA don't support this kind of a hot plug. But as long as you give different application or different process, you can stop it. So there's a few things I want to emphasize. If you have two different processes, and then your second process want to have from 2 GPU to 4 GPU, you only need to stop second process because it's adding the GPU for that. So it's the most important is the process what you are running. It's not hard pluggable. Underneath that, everything is hard pluggable. Yep.
Yeah, but you are showing two completely separate system images there, right? That are sharing the same network of PCIe switches so that they can reach the same set of GPUs, right?
No, yeah, I need a little bit more explain. Okay, good questions. Let me go back to. It's good because with the discussion, it's easier to understand the PCIe because I think PCIe hot plug is not a very it's very new. It's not existing in the industry for a long time. I use this as an example that when the device we have the firmware in the GPU box. The GPU box do the PCIe emulation to the host. So when like power, when they do the ski boot device scan, we will extend to reserve more device bus number and the bar 0, bar 1, bar 2 memory address. That is reservation is for the GPU. Because you know the different PCIe devices that have a different memory address required, virtual memory address required. So we ask the biggest resources in order to do the GPU hot plug. So usually in our implementation, we ask 18 bus number, and each bus number we ask 32 gigabyte memory address because of V100. Yeah. So every host, when he scan it, he will reserve that kind of resources in every PCIe Gen4 connections. So when we assign a GPU, it will looks like someone plug one GPU on the virtual bus number. So we do the emulations for the host. So that's why that we can, yeah. Then there's above. Underneath, we also virtualize all the PCIe devices. Then the PCIe devices, they won't see each other's. It's been virtualized by our management CPU. So it's been all okay by our CPU. So it means that they don't know there's a GPU there. Okay. Any other questions?
So you have the management CPUs, is it Falcon?
Yeah, in the Falcon II, yes. Yes.
How many?
It's just one. Each chassis is just one. Yep. So this is the Composable AI's motivation. We see the second motivation is like this. It's in the rendering industry, they have interactive rendering in the morning, in the daytime. But they want to consolidate all the GPU in the nighttime to do the batch rendering. So at that situation, it's very difficult for them to find a good machines to fulfill that kind of requirement. So they use like 4 machines and one this kind of box to allocate the GPU in the morning to all the server. And then during the nighttime, it consolidates all the GPU to the most powerful 1 or 2 server to do the batch rendering. Okay, so this is 2 major modifications. I think I will talk a little bit about this. Except that there's another application, except I just say that you have a different algorithm to do the AI. Except that they have to do another things. They want to do the core scalability test. Usually you use 1 core and more GPU scalability. You have a core and you can put in a 2 GPU server. It could run well. But how about put a GPU server? Does the code really take a GPU power to do it quicker? So they also do this kind of experiment and to see how the code scale. And also the GPU, the code operate in different heterogeneous computing environment. For example, this working in NVIDIA CUDA and AMD OpenPOWER, and also in Xilinx environments. They have 3 different environments. But it's difficult, again, to put all of these devices in different server and ask people to move. So they put it in the same in a box and assign to another host to test. There's a code moving to different devices to see the performance. Okay, so the AI not just because of the algorithm different, it's also because of the device difference and also the scalability. So there are 3 major motivation in a composable AI. Okay. This is from Cisco. Yeah, that's talking about the whole interchange starting from the very integrated machines and until composable. So this is a technology trend that everybody wants to disaggregate things because in the future it's data-centric computing, not system-centric or CPU-centric computing. So that's why you want to disaggregate all the devices and then try to leverage their flexibility and make the data to be compute at a data place. Okay, so you see that IBM also talk about the memory disaggregate in the Power 10 because they want to make it a memory. Memory usually is data. In fact, memory-centric is data-centric. It's the same. So they want to do that things too. Okay. And of course, that part is the most difficult part. This is the architecture. I just explained a little bit about how we reserve the resources and how we emulated the PCIe resources for the server. And then when you do the hot plug, then the device will be there. And when we remove, then don't need shut down all the system. But there is some limitation. In fact, there are 3 different limitations. I mentioned a few things. The first is a skip boot or x86 BIOS. They need to support that under one root complex as a multiple devices and multiple bus number is allowed. In lots of implementation, they don't allow it because they think there's no way you ask so many bus number and the resources under one PCIe by 16, no matter Gen 3 or Gen 4, in our experience. But now people is getting, knowing that in the disaggregated architectures, especially in NVMe, the bus number usually should not, in some way, you by 16, you probably give in 8 NVMe 68. So it probably can give 8, but usually it's very difficult to give 18. This is the first problem, the resource. The second thing is that the driver itself, the device driver, whether device driver is allow the hot plug or not, I think it's lots of people know if in the past, if a PCIe device die, you got a blue screen. There's any PCIe device die. If they talk about like 4 years ago or 5 years ago, if any PCIe device die, it's a blue screen. Then Now, I think this no longer to be a problem because 2015 or 2016, the industry already worked on the Linux kernel mainstream to solve that issues. So, but device driver is still the problem. The device still need to allow the device to be added in or removed. Okay. Then this is the key issues of the implementations for this kind of architectures. How many resources could be allocated, and the driver. So this is but we see the industry already solved that issue a lot. So we work with the x86 and now in the OpenPOWER, if you manage the ski boot, it will be solved. At x86 already, most of our servers should be okay. Okay. So this is the chassis. I just very quick give you a chassis just for you, 16 GPU. It's a lot of density of the GPU, and we have a very great cooling design. It's, in fact, it's made by Wistron. It's IBM's hardware partners. We just made the software, putting our software on top of this box. Okay. The software feature that we do in this box is that we can do dynamic allocation of the GPU to CPU. Basically, in fact, we can do all the devices. I mean, like Mellanox Connect 4, Connect 5. We have do it in IBM. IBM use Connect 4 and Connect 5 to manage all the GPU cluster. Okay. Also do the Samsung nbsp. They also put the Samsung nbsp in it. We also put in some of the Intel bifurcation card or some kind of AMD GPU. We putting a lot of things in this kind of a PCIe box. As long as it's a standard PCIe, then it could be used. However, some of us different functions, probably not an industry standard. Its option standards would be some compatibility issues. For example, if you have an option ROM, you need to boot from the option ROM. That is some problems in the PCIe devices. Okay. So we also do the hot plug as a PCIe device. It's like I just explained, we emulate a PCIe device to the host, and we do plug in and plug out to do dynamic allocate. So for one server, it's plug in. For another server, it's plug out. Our PCIe port could be a host or device port. And we can also do the performance monitoring. Performance monitoring, like I talk about in the keynote, because the problem is that lots of people think it's, the GPU is very busy. But in fact, there are three factors and the so-called GPU busy. It's whether it's I/O or memory utilization or it's core utilizations. Usually what we call core utilizations, very few people can reach over 35% in our partner experience, I mean, including IBM. I mean, how they calculate is they calculate the whole month, including the holidays, including the night. It's in average, it's very difficult to reach over 35%. So there's one the most important motivation for this part is that if we can give some of the flexibility plus management information from the box, because there's some difficulty to get the information from in-band, because most of the time the algorithm or the data set is confidential. There's no one can really touch the systems except the people who do the AI, that small team can touch the system. All the other people cannot touch it. So, but you cannot touch it. How can you get the management informations? So we do it from the box outbound to monitor the data transaction, to monitor the core utilization, to monitor the memory utilization. With that, the developer and the system administrator know how to better utilize the core, know how to better utilize the hardware resources. Then we also, of course, we do the P2P and the management GUI. Any question now? If not, I go to see the demo. Yeah, 尽量你先上来做准备. Yeah, please.
How do you connect from the server to the I/O box?
Oh, sorry, I did not explain it. We use the CDFP cables. CDFP cables has been well used in the networking industry, and it's around 25 GT per second. So Gen 4 is only 16 GT per second. So we run that one to use the run PCIe Gen4 protocol. So there's a cable is up to 1.5 meters long. So theoretically, it's in a rack. It's not able to close the rack. If you except it's just next to the rack, probably it's also okay.
And how do you say which card is going to which server?
Oh, yeah, good questions. Yeah, later on our demo will show you. In fact, we have a topology. That topology can know which server being connected to. Oh, we build up a management software on another virtual machine on another server. He will read the box will report what the connection and the devices available to that management center. So that management center know all the topology and all the available resources and which resources physically in which slot being assigned to which host. And then they have the same UUID, so they know on the if there's one device fail, it's easy for you to track which slot has been failed, which device should be changed.
So it's in a different console from the...
Yes, it's different. It's a different machine because, yes, it's like a management software. It's like management software is installed in another VM machine, and that VM machine collect all the information from all these machines, so he can draw a topology. Yeah. Yeah, it's like IBM storage systems management GUI, similar like that. You have a cluster, you have all the cluster, you have different machines, you have a different host and a different storage. And then you know the connection of a different storage.
Yeah, you have the ASMI. It's
Yeah. Not the HNC.
The HNC
It's not HNC.
The hardware.
HMC is, yeah.
It's behind, it's the small little box inside of the server. Yeah.
No, it's not HNC. HNC is built-in internal to talk to each other. But yeah, similar to HMC, a little bit. Similar to HMC. Yeah, HMC. Yeah.
Can I use the HP Falcon II in order to do the same as the GPU, but with an FPGA card?
Yes, sure.
And the box not only works with GPUs, I can use it with FPGA cards?
Yes. But here I want to emphasize, if using FPGA, there's encounter lots of different compatibility issues. For example, the thing that I just explained that I can get core utilization information from I2C. Different FPGA have a different implementation way, so there is some probably need to integrate in the box in order to make it work. Any questions?
So you have a management VM running in any of those four systems or even outside. How are they communicating to the management processor inside the Falcon II? Is it in-band communication through the PCI links that you have already, or themselves, or through TCP? And how do they communicate?
We have our OS installed in the BMC of the Falcon II box. So the BMC will report all the information through BMC 1 gigabit management port back to the management center. So the management center know everything of the machines.
Okay, so there's a BMC on the Falcon II as well.
Yes.
You communicate through network.
Yes.
IBM,
Yes.
I think that the management board is IBM, right? example, if I need to add a new box, HP Falcon, I imagine that you log into the GUI web,
Yes, yes.
and that via the management board.
Yes, 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 it is. So what the information that we collect from the, in the system-wise, of course, we collect also fan information or the power information, but we also connect it to the I2C of every single slot. So we collect all the information from single slot. I think I2C spec open spec is more complete in the NVMe, the most complete. NVMe have NVMe spec have been defined, so it's very complete. And then NVIDIA have their own proprietary implementation way to give the information from the I2C. Yep. You mean if we do the dynamical locations, we don't?
Right, so if you have two different systems there and you have a GPU assigned to one, you unassign it and assign it to a different system, is that, how do you ensure that GPU memory is cleared and such? Is there power control on those slots so that you power cycle it across those sort of events?
No, we don't do that. I think it's GPU driver will do that. They know they lost the GPU driver will know it. I will lose it.
But when submitting jobs, you need to configure those jobs to use specifically the set of GPUs that
Yes.
the management system is determining it to be, right? Because
Yes.
if the management system does something wrong, the PCI bus that you have will allow two different system images to try to access the same GPU at the same time. And that will blow things up, right?
Yeah, so there's good questions. In fact, we have some preventing mechanism. If you want to remove one GPU from one server and assign to another server, if we find there's some utilization and some throughput, we won't double, won't twice say, are you sure you want to remove? Because we see the number. If you remove, some process will be killed. But if they want to remove, then it's just removed. So we haven't, because theoretically this is being used by the administrators. They should know this system very well. It's not being used by user, because user usually, if they do it, then well, it's a disaster. So usually used by administrator, then administrator know how serious of the effect. So we will provide the information to them, say, hey, look, someone is still using.
Intelligence category.
Yeah.
You have a management tool you said that runs an EM to manage the assignment. Is there also a CLI that's available?
Yes, yes. In fact, we have a GUI, we have a Redfish, and also the RESTful. We have that kind of a standard that you can use. So the demo environment is that we have the environments in Taiwan's research. Our research environment. So you will see some of the data that we just using, but we are not doing all the information because we cannot. They are doing some stress. You will see some of the data transfers in it, and then of course there is our implementations. So later you will see the management GUI and how we monitoring the performance and how we provide some measurement information to the center. Then you can see it. Any other questions?
Yeah, just a little more.
Okay, thank you.
Why? Maybe need to use your laptop. 这个不行。对。
为什么？
对。然后去。
也为了么？
然后再调一下。看看。 它那很像歪掉之类的。
那不然你用我的东西都给你。
对啊，不用。
那我，那你先都给你们。This time I explain a little bit of the architectures because in the IBM usage they use normally it's 4 server connected to 16 GPU, but it's closed. So it means that they could up to get 28 GPU or 4 GPU. In average, it's just 4 GPU normally, but they can get it. So in their usage, like 4 GPU, 8 GPU, or 16 GPU, or 28 GPU at the same time. They also see the locality, because the locality is very important. In their experiment, they shows that if, because the P2P is within the PCIe tree, right? So it's we do the memory address translation, so they don't go back to the system memory. If you go back to the system memory, they see even it's on the same server and go through low complex QPI, it's what decrease at least 20%. If you have for example, you have 8 GPU, then 4 GPU on one CPU and another 4 GPU on one CPU. If you go this 8 GPU to do the P2P, you will go through the QPI. It's at least reduce 20%.
Like the Newman connectivity between the communication between the CPU and the memory. It's the same that you are speaking about with GPU, right?
Yeah, it's because the memory here, if they want to do the P2P, it's if there's a 4 GPU memory to do the P2P, it's communicate through the PCI switch. But if they want to communicate with the other 4 GPU, you need to go to the CPU, QPR, and back to the yeah, it's 10% mostly here. So the locality is one of the key issues why they choose the PCI as a composable. But of course, PCI
We can't hear you.
oh, sorry.
That's fine, just speak into that.
Oh. But PCI have his limitations. The key limitation is the scalability. You can if you want to over 30 to 64 GPU, it's very difficult to use GPU PCI Fabric to do it. It probably can reach 16 is good, 32 probably, but 32 is already crossed another CPU. 16 is the highest that it stay in the same PCI Fabric in our current implementations. So that is the limitation of the scalability of the GPU. But the locality is, there is got another very bad number if they have another test. If they test 4 GPU in a single PCI tree and each server get 1 GPU, at that scenario, the performance is just reduced to only 30% of the 4 GPU on the same PCI tree. Because you can imagine that a lot of time is just waiting the I/O to the backward and the forward and backward synchronizations, that kind of things is waiting. Yeah. Okay. So, yeah, we have some connection problem here. Wait a moment, I can do it. Any questions?
Oh, the magic dongle.
I changed to my mobile phone network, and it's work.
那我这应该可以，
那你可以玩，你那边可以玩。
去
那你就拿这个，那你用那个。
那个完全不行。
Have anyone tried PCIe composable? No? Only use the Ethernet or okay. Finally, we got it.
Okay, this is the Falcon II GUI. So the Falcon II has two identical PCIe drawer. So okay, here is drawer 1 and the drawer 2, and each drawer can put a GPU and 2 host connection. So now drawer 1, we put 2 P100 and 1 T4, and also 1 NVMe. So now there are 1 host connected to this PCI switch. And I'm going to show you the GPU hub block. Let me go into the server first.
Here we put the GPU in different PCI switch. We do it on purpose because then you do the P2P, then you can see it's going through the different PCI switch. And we also put the different PCI devices.
Okay, this is the PCI topology here. And this tree is from the Falcon II. In order to support the PCI hub block, so we synthesize some PCI downstream port here. And to get a PCI resource from the host server, like we asking host server to reserve some PCI buses and also PCI memory mapping resource. So that's why we can do the PCI hub block. And you don't need to shut down the host server or reboot the host server. Okay, now it's no GPU here on this server. Okay, no GPU here. Okay, I'm going to assign 1 P100. Okay. Host detect 1 P100 here. And we check the PCI tree. Here, P100. And also we using the NVIDIA SMI to check. Okay, 1 P100. And now I'm going to assign second one. P100. Okay. Also 1 SSD. Okay, check the PCI topology. 2 P100 here, and also 1 Intel SSD. Two P100. And 1 Intel SSD here. Okay, I'm not going to do the direct memory access between these two GPUs. And on this page, we monitor the PCIe traffic and also monitor the PCIe error status. So let's run. Let me run the program first. I'm doing a memory copy between these two GPUs. Two-way memory copy. Okay, we can check the traffic here. Okay, it's now strongly. So we can see the GPU ingress and egress data traffic between these two GPU, this P100 here and here. Because it's peer-to-peer, so the data not go through to the host server memory. So host memory traffic is no traffic here, only between these two GPU, here and here.
Communication between the same PCIe, right?
Yeah, PCIe.
That's why we don't see too much throughput to the server, right? Yes.
Okay. This is traffic ingress and egress here. And we here on this page, we also monitor the PCIe error status, like transaction rate packet error or data link rate packet error. And we also monitor device receiver error count in order to get a better performance. So we will monitor each PCIe port error status. Okay, that's the demo.
May I ask one final question?
Yeah, sure.
I know we're out of time, but this is a lovely demo. My one question is, what things aren't you doing today in the box that you'd envision doing? You know, what's next in your technology and your roadmap? Have you thought about that? What do you want to do with this? Besides sell lots of it and become famous, right?
We want to do all the device or all the memory mapping through the PCIe. It's like Intel CXL kind of things.
Oh, okay.
Yeah, because all the PCIe device, if they are under the same, I mean, of course, we can cross different MCPU domain. And basically, in this MCPU domain, he will submit his device memory mapping to all the PCIe Fabric, all the hosts. So all the hosts, although the device belongs to one of the hosts, but their memory still can be reached by other devices or by other CPU. Yeah, that is what we want to do in the future, because it will be suitable for the PCIe to shoot for that kind of target.
Thank you.
Thank you.